All right, so let's go ahead and talk about today's lab. So today's lab is lab number 7, and we frequently call this our green acid lab because we do use green acid, and it is not something super toxic. We just add some food coloring to it, and there's a reason we add the food coloring, and it's so that you can see it inside of your setup here. So I think this is a fun lab, but it is a little tricky to get set up, so you luckily get to skip the setup part. So what you would do is take your funnel right here, and you would attach it to glass tubing that we would give you. And here is that glass tubing. And then you attach it to something that we call a drying tube. And inside of that drying tube is where the reaction is going to occur. And yes, I am recording. Let's just double check. Yes, the recording is going for the lab. Yes. All right, so inside of this drying tube is where your reaction is going to occur. You'll have a piece of metal, and you are going to put, or you would put, a copper cage around it. So it is copper mesh right inside, and you would take that copper mesh and you would wrap it around your metal. The bad thing is sometimes that metal is a little sharp, so you have to be really careful as you fold it over not to prick your fingers. But the idea is you're creating a cage of copper that's going to surround your metal. So as your metal starts to break down, you're not going to lose any pieces. Without that copper cage, pieces of your metal could break off and float away down the tube, really in any direction, but most likely they would go through that tube into the flask there. All right, so here is your chemical reaction. And what you'll be doing, or what you would be doing, is producing hydrogen gas. And that gas is going to flow through this tube right here into a flask filled with water. So that flask, you would fill it completely with water, and you would measure how much water you put in there. And then as the gas is being formed, it's going to come up, and then it will sit up at the top because it is less dense than water, so it's going to force some water out of it. So the way that you'd find out how much gas you generated is by taking first the total volume of water you had before the experiment started, so how much total water could fit in there, and then what you would do is measure how much water was left afterwards. The subtraction of those two would tell you how much air, how much hydrogen gas you generated. So that's sort of an overview of the experiment. So now let's talk in more detail. So any questions so far about the experiment before I go on? All right. So again, you're going to put an unknown metal in a copper cage. And so we're going to give you data, and it's going to be your job to figure out which unknown metal you would have had, or this mystery student had. You're going to react it with hydrochloric acid, and that acid is dyed green, so you can see it traveling through here. Now during the experiment, it's going to be important that you don't let the acid or the water go below the clay triangle right here. So the very first thing that you would do is you would flush this through with water. So you would add water here, let the water flow all the way through, and you'd be pushing out all the air bubbles. Now, if you then allow your water or your acid to get below the clay triangle right over here that's holding your funnel, you could be getting more air bubbles in there. And today we're measuring the air bubbles, so the last thing we would want is extra air bubbles. So once you flush this entire thing through with water, then you would start adding your acid. And again, you're going to have green acid for this experiment, hence why we call it the green acid lab. And it's going to come down to this pinch clamp. And this pinch clamp is kind of the funky thing in your drawer that everybody asks, what is this? It is actually to stop the flow of the solution. So you would very carefully pinch the pinch clamp, and as you do, a little bit would flow through. So you would have to be very careful pinching that pinch clamp, let a little run through, and then stop, pinch a little bit, let it come through. And the idea is you're going to let that green acid come through very, very slowly, making sure you never run out up at the top there. So it kind of takes two partners, one who's letting the acid go through, the other who's monitoring to make sure you always have enough acid in the funnel up at the top. When that acid hits your sample, that is when the bubbling will start. And that is when the gas will start bubbling on through here. Now, the way I drew it, it looks like it's flooded with gas. That's not really how it happens. It goes bubble, bubble, bubble. And normally what I would tell you is try to get a good bubble going. If it's going very slowly, it will take you hours to do this experiment. And I would normally tell you that I don't want you to have to stay till midnight working on this experiment. So I would be walking around and making sure that you have a good flow of gas coming off of that. So we don't want it too fast. If you have it too fast, what you would see is all kinds of craziness swirling inside of here. So you'd see all sorts of craziness swirling inside of there, and one of the craziness things that you might see is a piece of your metal trying to break free of the copper, and it might start trying to travel. So we want a slow bubble, but a nice, slow, consistent one. We want it to go bubble, bubble, bubble. We don't want it to go bubble, wait 5 minutes, another bubble. That's a problem. That's when you would be in class till midnight. So again, during the lab, I would be walking around to make sure that everybody was getting a good flow of gas through. So here it says, when you flush with the water, make sure the tube is not inside of the flask. So the way this part right here is set up is you would be given a tub and you'd fill that at least halfway with water, and then you would need to fill this entirely with water. And it takes a few tries for most people, although every once in a while we have someone who is super awesome. They fill it with water, you put your hand on the top of the flask, and then very quickly you have to invert and dunk under the water without losing any water. So then what you'd be looking for is any air bubbles up at the top. So a little air bubble like so, that would be up on the top. Usually it hangs on to the sides, and if that happens, then you would do it again. And so sometimes it takes a little while to get a really nice fill where it fills this one completely, but that is our aim here. And so the purpose of making sure this tubing right here is not inside when you flush the air bubbles out of the tube is that we don't want to add any air until the experiment actually starts. So sometimes it's a little tough to get this to stand up correctly, and so what I always recommend is that you actually lean it kind of against the side here. That's a terrible version of an Erlenmeyer flask. That's still a terrible version, but let's just imagine it's not. All right, my recommendation is usually that you lean it a little bit on the corner to help stabilize it. But during the experiment, you always have to make sure it doesn't fall over, because if it falls over, it's going to leave. It's going to lose its gas, and that is going to mess up your experiment. All right, so at the end of your experiment, we need to get your flask out of the water, but we want to equalize it first. So if we imagine, this is another horrible drawing, I apologize. This is your flask, and this is the water down here. We want the level of water inside the flask to be the same as the level of water in your tub. And there's a reason for that, and it goes way back to our manometer days. So back when we were doing manometers, we said if the level of mercury on both sides of the manometer was the same, H would be equal to 0. And when H is equal to 0, the pressure of the gas was the same as the atmospheric pressure. So in our calculations, we want to be able to make this assumption. So we need to equalize our water levels. The way you would do that is to tip this on its side, and now the level of water inside the flask is equal to the level of water inside of the tub. And at this point, that's very interesting. I don't know why that's not working. Okay, I will have to figure out. Oh no. Why my eraser and highlighting tool aren't working. Okay, and either way, what you would have to do at this point is put your hand over the mouth of that flask and very carefully write it again without losing any water. So normally you put your hand on there, kind of create a little suction under the water, and then very quickly, and then you'll be measuring that water to see how much water is left. It's very strange. There we go. Okay. Questions on anything there so far?
Hello, this is Dr. Die. I'm going to demonstrate how you're going to be doing this experiment to find out the equivalent weight or equivalent mass of an unknown metal. If you were doing the experiment, you would be receiving several items from the stockroom. One of them is a big tray here that you're going to fill with water, probably like 2/3 of the way up. Okay, I'm going to put this down here. All right, and then you're also going to receive some interesting sets of tubing. One of them has what is called a desiccator tube on one end. It's a tube with kind of like a bulb in it, and as you can see, several connections, including a curved glass tube at the end, and another kind of like a J-shaped kind of tube that has a stopper on the short end and just a hose on the other end. You'll also receive a thermometer, and you're going to be picking up a piece of metal mesh that you're going to use, and also a very tiny piece of metal which you will want to weight. So I'm going to use one of these little plastic boats so you can weight the metal. You can see it there. Let me pick it up so you can see it a little better. Okay, so it'll be kind of like a little piece of metal that you have in there, and you're going to take the mass of that. All right. You're also going to have to obtain something called green acid. Now, let me explain what that means. It's actually just 6 molar hydrochloric acid into which we've put a little bit of copper 2 chloride to give it a green color. That's so you can track it during the process. Now, you're not going to pour from here, so as usual, you will bring a small beaker to the cart where this is going to be at, and as usual, just you don't have to be exact here. You're going to take approximately, I don't know, something like maybe 30 to 40 milliliters. Just remember to pour with conviction, or else it'll start dribbling down the sides. Okay, and you're only going to need something like 30 to 40 milliliters of the green acid. I'm going to put it here on the side for now. Okay, now what you need to set up is the following. This is the apparatus that you're going to set up. It's on page 20 of your lab manual, so you might want to refer to that picture as we walk through the following set of demos here. Okay, now you need to get yourself a ring stand. And on the ring stand, you're going to put a clamp, and you're also going to put in a iron support ring. The iron support ring will also require you to put in a clay triangle, and on it, we're going to put a glass funnel, and that'll hold it in place. Okay. Okay, the next part of your assembly consists of attaching the J-shaped tube very carefully here. Again, remember, always twist the rubber hose into the end of the funnel. Be careful not to, break it or cut yourself. Okay, here we go. And then what we're going to do is we're going to attach the desiccator tube kind of upside down into this clamp. Once more, hold it just tight enough that it will not fall down. You want it to rotate around a little bit. Of course, you don't want to crack the actual glass in there. Notice that the other end of this should be long enough to be in a position where it can go into the reservoir here. So I'm going to move this reservoir over a little bit here to make sure that it's going to fit in there. And I also want to be able to make sure that this thing can turn. Okay? So after having weighted my piece of metal, all right, and again, in my data sheet, I need to make sure I record that mass over here on the top where it says mass of your sample. That's your metal, all right? What I'm going to do is I'm going to take the piece of metal and I'm going to put it inside this copper mesh. And the goal here is to kind of wrap it in the copper mesh, all right? I'm going to make like a little cage for it. The goal of this is that during the reaction, as the metal reacts with the hydrochloric acid, it'll start shrinking, of course, as it basically gets corroded away. And you want to make sure that all of the pieces of metal stay there till the very end, that they don't flow through. So we're going to do this. And then what I'm going to do is I'm going to put it underneath here. And while I hold it in place at the mouth of the desiccator tube, very carefully, I am going to place the stopper part of the J-shaped tube. And once more, you want to twist the tube into the stopper to generate a good seal. You want it to be very tight, all right? Again, never push on the glass. Always push down into the stopper by twisting. And now I'm all set. And what I want to do now is I need some water to chase this with, all right? I want to generate, again, a siphon of water all within this system that goes all the way to this reservoir. So you're probably better off taking a beaker of water from the sink. I mean, it can be tap water, okay? And have your pinch clamp ready, because when this whole thing fills up, I want to hold it in place, all right? So I'm going to start pouring the water. That way I can check that there's no bubbles trapped in the system. I can check that there is no leaks. And once it's full, I'm going to clamp it. And I'm going to inspect visually, make sure there's no water leaking out of anywhere. Make sure there's no bubbles. So you might want to squeeze a little bit on this thing at different points. Make sure there are no bubbles anywhere. Okay. So my system is now sealed. Let me see if I can turn this around so you can see it a little better, perhaps. There you go. So there is your desiccator tube with the piece of metal in its copper mesh. Remember, copper is resistant to HCl, so it's not going to react. But the metal you have in there will. Now, the goal of the experiment is to wash hydrochloric acid through so that when it reacts with the metal here, as we saw in the introduction, hydrogen gas will be produced. The hydrogen gas is less dense than water, so it'll basically come to the top and essentially get pushed out. So we want to harvest this, and what we're going to do is get a large flask, fill it with water all the way to the very edge there. And then what I do is I use a big rubber stopper, and I kind of slide it in to make sure I don't trap any bubbles in there. Okay, I don't want to have any bubbles in there. And then what I'm going to do is, while I'm holding it, I'm going to invert the flask into the reservoir here. Again, making sure I don't trap any air bubbles in there. And once it's inside, okay, I can remove the stopper. There's the stopper. And now my flask is inside, completely filled with water. And now what I'm going to do is I'm going to take the curved tip of my tube here and kind of slip it underneath so that it's pointing inside the flask. All right. Now, if you're doing the experiment, you want to place this in a way where it won't slide off or fall down. Okay, you don't want it dancing around. So probably what will happen is during the experiment, you may want to have maybe one of the teammates here can hold the flask in place while the reaction goes through, just to avoid any sudden vibrations to kind of like jar it loose and make it fall into the water and then cause you to lose your sample. Okay? So I'm almost ready to start here. And now what I'm going to do is I'm going to open the pinch clamp and let the water drop to basically the bottom of the cone of the funnel here. All right? And now very carefully. You don't want it to go too far down because you don't want to trap any air bubbles in here. All right? There we go. Now, if you have a little bubble, it won't matter. The issue is you don't want any big bubbles because they'll interfere with the flow of the acid and of the hydrogen gas product. Okay? Remember that we had this beaker that had the acid in it. So I'm going to pour in maybe about 20 milliliters or so of the acid. The acid is denser than water. So once it hits here, it's going to start migrating down. Okay? So tell you what, I'm going to bring this down a little more. I want it right at the very bottom of the cone of the glass funnel, and now I'm going to put in about half of the sample that I have here. Okay, I'm going to put in there. And the idea of the green color is that you can watch it migrate down the tube. Right now, what you'll see is some kind of like wavy patterns. Those are called Schlieren patterns. It's an optical effect of the mixing of two solutions of different densities. So right now, what I'm going to do is I'm going to open the pinch clamp and allow this acid to flow again all the way to the bottom of the cone of the glass funnel. And as it goes down, it's going to start moving down and it's going to start reacting with the metal. And you'll see the metal start forming bubbles. Let me see if I have something here that would allow you to see that. Probably not. But it is foaming ferociously here. All right. Right there in front of my hands. And as it does, it starts producing hydrogen gas that is going to start migrating up this tube. And it's going to start bubbling into the water inside the flask. Okay, so I'm going to let it run a little bit here, and while we do that, we will take a little pause in the video here. Okay, and I'll be back as soon as this is finished reacting. All right. Okay, we are back, and at this point, you see very little bubbling happening. One of the things that may happen is that the liquid here above where the metal was has gotten very dark. That's because our copper mesh was probably dirty, had other oxides and stuff in there that got kind of removed. So what I want to do now is I want to take some water and give this one final chase to get rid of all the hydrogen product in there. So I'm going to fill up the funnel here with water, and I'm going to chase down everything that's in there, all the reaction mix, make sure all the hydrogen is collected. There's no more stuff in there. All right, so I'm going to give it a good chase here, and now there's no more bubbling. I've gotten rid of it. I want to make a visual inspection to make sure that all of the metal is gone, so it all reacted. And so now what I have is in my flask over here, I have a collection, a big bubble of hydrogen gas in there. Of course, you would be doing this in the fume hood to make sure that everything's okay, and you would be taking care of things here. So what we're going to do now is we want to measure out how much water was left in the flask. And I just realized that. Oh, hold on a second. Oh, here it is. Sorry. Once more, this is your apparatus. On your data, you wanted to make sure that you put in the volume of water left in the flask, the temperature and stuff. But remember, the idea here is I want to know how much hydrogen is in there by knowing what is its volume, what is its pressure, and what is its temperature. Okay? So what I need to do is equalize the pressure. Remember that we're going to use a barometer to register the pressure of air on the water here So we want to equalize that with the pressure of the hydrogen inside the flask. So what I'm going to do is I'm going to hold the flask very carefully remove the little tubing from here. Once more, bring in my rubber stopper. And what I'm going to do now is I'm going to tilt the flask. All right, I'm going to tilt it until the water inside is at the same level as the water on the outside. And once it's there, I'm going to slip in the rubber stopper and cover it and then pull it out. All right. And at this point, what I have is, as you can see, there's residual water, and over here would be hydrogen, of course, mixed with some water vapor, which we'll have to compensate for later on. All right. At this point, because there's hydrogen here and it's flammable, I want to keep it away from sparks. So I'm going to, do this in the fume hood. I'm going to open this. Okay. So I'm going to open this in the fume hood. I'm going to let the hydrogen just vent out. And now I'm ready. What I'm going to do is I'm going to bring my thermometer. I'm going to take the temperature of the water in here, because it should be the same as the temperature that the hydrogen had before. All right. And the next thing I'm going to do is I'm going to take a graduate cylinder, one of the large ones, and I'm going to measure the volume of water in there. All right. And then what I'm going to do is I'm going to go back to the sink. I'm going to fill up the flask, and I'm going to read what is the volume of that. The difference between the total volume that the flask has as its capacity and the volume of water that was left in here, that would be the volume that the hydrogen gas was occupying. All right. Couple of things throughout the procedure. For example, let's say that your rubber stopper here was not very properly sealed and you had a little bit of a leak of acid. Don't wipe it. You had to bring some sodium bicarbonate, some baking soda to neutralize it before you wipe it clean. All right. Once we're done, of course, we've flushed the system with water. The acid has been tremendously diluted in this reservoir here, so we don't need to worry about that. So very carefully, what we'll do is bring in like a waste flask, and you can put it underneath here and be ready to open this and take back your piece of metal. Make sure you return the copper mesh back to the stockroom. All right, so I'm going to open it here very carefully. Okay, and I'm going to let this kind of flush down. There we go. There's my piece of copper metal. So I'm going to pull that out so I can give it back to the stockroom. And the rest is going to be cleanup of the stuff here. Okay, thank you so much. In our next video, we'll walk through some sample calculations.
But let's go ahead and go on to our calculations. So here, the first one is going to be the mass of the sample. So these are individual pieces of metal, and so what we ask you to do is first to put a little newspaper on, our little cutouts of newspaper on the balance, hit 0 or tear, and then place the metal on there and find out how much your metal weighs. Next up, you're going to need the flask volume. So just like the video from last class showed you, you would fill that flask entirely with water and then pour it into our large graduated cylinder. Pressure you would measure from the barometer in the room. And then temperature is going to be the temperature of the water in the flask after the reaction. So after it is under the water, you put your hand on it, you ride it up. Sorry for the sound effects. I would recommend you take the temperature before you pour it into the graduated cylinder. All right, and then finally, the volume of water left in your flask. So 1 through 5 here, you're going to be given on the sample data. So you're given data for 2 trials here, and this is already on our website under the lab notes section. And just like always, I want you to write it onto your own page in pen. If you don't have the lab, then go ahead and write it on another page neatly in pen. And this is the only section that has to be done in pen because this is the data, the results that we're going to talk about next. If you want to do it on pencil or iPad or wherever, that's perfectly fine. All right, so any questions about anything so far? All right, so next up, volume of H2, the volume of our gas. And notice everything here is numbered. So flask volume minus the volume of water left in the flask. So you're going to take the total amount of water that was in the flask minus how much was left over. And that is 2 minus 5. So right up here, 2 minus 5 there. So any questions about that first calculation that I've numbered 6? All right, so number 7 there, you're converting your temperature from the flask into Kelvin. So you're adding 273.15. Next up, you need the pressure of water. So the G after it is not grams, it is gas. For a minute there, I was wondering why we had water in grams. It is water and gas, and that is in torr. It came from your lab before, I believe it was lab number 5, but I've copied it down here. It is this table right here. So let's imagine that you were given a temperature of, 26 degrees Celsius. You would then say the vapor pressure was 26.7 torr. This table gives you torr. All right, so any questions about getting the pressure of that water gas? That's the vapor pressure of water from that table. All right, so next up is pressure of hydrogen gas dry. We've done this once before. We talked about the idea of collecting gas over water. We know that a little bit of the water will vaporize and get in our way, so we have to do a subtraction. And here's that subtraction. The room pressure, which we have numbered as 3, minus the pressure of water, which you just found on the table, which is numbered as 8. So any questions about finding the dry vapor pressure, or I should say the dry pressure of hydrogen gas? All right, so next up is the molar volume right over here. And so it says see next page. This one's a little bit of a trickier calculation. So here is number 10, and you've done something like this before in a previous lab. So I'm starting off with our PV equals NT over PV equals NT. So the number of moles won't change, so we have crossed those out. And now you have pressure times volume divided by temperature equals pressure times volume over temperature. On the left you have, lab conditions. On the right you have STP. So on the left, for pressure, you'll put in what you had for number 9. For temperature, you're going to put in number 7, so that should be your temperature in Kelvin. Now on the right-hand side, your temperature is 0 degrees Celsius, but you need to convert it into Kelvin. The pressure will be the standard pressure, and I've noted here 760 torr. So whenever we use our PV over NT equals PV over NT, you have to keep the same units for pressure on both sides. Since number 9 over here is going to be in torr, you want to use this 760 torr, and I realize I've got orange and I'm highlighting with orange, and that's probably terrible. I apologize. All right. So we talked about the pressure and the temperature. Next up, let me try a better highlight color. Next up, we need volume, and the volume you're going to use for STP is our known molar volume, and that is 22.4 liters per mole. So that's what's going in for volume on the right side. There we go. All right, what you're solving for is this right here. So you're going to solve for V1, and again, you have all of the other values. So any questions on how you're plugging into number 10 here? So this is probably the trickiest calculation in this lab. So some of you are thinking, wow, it'd be so boring to leave class early. I would just love to stay till 9:45. You might want to stay and just work on this lab, get this done, at least the first trial. That way you'll know how to do it. And just a reminder, this lab is not due until Wednesday of next week. So you have a whole week to work on it. All right, so we just talked about calculation number 10 here. Now, calculation number 11. So 11 is also a little weird. So what we're taking is the volume in liters divided by the molar volume. So in other words, you're going to take number 6, which is your volume of hydrogen. You're going to divide it by 1,000. That puts it into liters. Then you're going to divide it by number 10, and number 10 was moles per liter. So this will get rid of your liters, and it will give you moles. And again, I know that's kind of a weird calculation to do, but any questions on how you're going to do number 11? All right, so next up is 12. And we've talked about equivalence way back when. And we said when we're dealing with equivalence, if it's an acid, we're dealing with H+. If it's a base, we're dealing with OH-. What we want to do is find out how many equivalents of H2 there are. So what we're going to do is take our moles of H2, which you found in number 11, and then we're going to use this conversion factor. And the conversion factor says for every 1 mole of H2, 2 moles of H+ were used. So that's how we produce the H2 gas. We used acid, which gave us the H+. But for every 1 mole of H2, you had to use 2 moles of H+. So essentially, you're going to take your moles of H2 and you're going to multiply them by 2. And that's going to tell you how many equivalents of acid were needed to produce the gas that you made. So again, I know that's kind of a weird one, but any questions on that? All right. Finally, we're going to do, or I guess almost finally, we're going to do the equivalent weight of the metal. And this is how you're going to figure out your unknown. You're going to take the mass of your sample, which was way up in number 1, so way up here. And then you'll divide it by your equivalents of hydrogen. And the equivalents of hydrogen were just above here in number 12. So that's how you're going to get your grams divided by equivalent. So how many grams for every 1 equivalent of H2? All right, next up, average equivalent weight. This is where you're going to take trial 1 plus trial 2, divide by 2, just like any other average. Then we want the percent difference. Trial 1 minus trial 2 divided by your average. And because it's in a percent, make sure you multiply by 100. And here you can just report the absolute value. You don't have to worry about whether it's negative or positive. Just report it as positive. All right, and finally the identity. And it says compare number 14, what you had above for your average equivalent weight, to the calculated values for aluminum and zinc in the discussion questions. And I'm going to show you how to do those in just a moment. But any questions on anything here, how you're going to do these calculations? All right, so let's talk about those discussion questions. So they're not too bad today. They're never too bad, actually. All right, so number 4 here says to calculate the equivalent weight for sodium, magnesium, aluminum, but those aren't all possibilities for you. You have only 2 possibilities. They are aluminum and zinc. So I need you to calculate the equivalent weight for aluminum and zinc, and then you will compare that with the value that you calculated above. All right, so here's how that calculation works. So first off, you need a balanced chemical equation. I'm doing it here with magnesium. Magnesium is not a possibility for you. I'm just showing you this as a sample. So here is your magnesium. You're reacting it with HCl and you're forming magnesium chloride plus H2 gas. So this is a single replacement and it's very important that you get that balanced. To calculate the equivalent weight, you're going to do grams of magnesium from the periodic table times moles of magnesium. And that moles of magnesium here comes from this right up here, divided by moles of hydrogen. And the moles of hydrogen are from the balanced equation. So here's your example below. So I have 24.305 grams. This is from the periodic table. And then I'm multiplying it by 1 because I only have 1 magnesium. However, if you balance something and you have a 2 or a 3 there, it needs to show up right here. All right, so molar mass from the periodic table times whatever your coefficient is in front of the metal, divided by the coefficient in front of the HCl. That will give you your equivalent weight, and you're going to find this equivalent weight for aluminum and zinc, and then you will compare it to your average equivalent weight here. Decide which one of those two it's closest to, and that's how you will decide the identity of your metal. All right, so questions on anything here so far? All right, so there's one more question that I want you to do. You get to skip part A because part A is basically what we just talked about. So part B is something that we've talked about before. So here you have a balanced chemical equation. You're given the grams of silver. And the first thing it asks you to do is calculate the moles of silver. So that's just a grams to moles conversion. And then it wants to know how many moles of NO gas. So that is a moles to moles conversion from your silver to your NO. And then finally, it's asking you what volume it will occupy. So if you know the moles, the liters, and the pressure, what formula would you use to find the volume? So what do you guys think? What formula would you use if you know the moles? Oh, there we go. PV equals nRT. Excellent. This is an ideal gas law. Yes. Excellent. For a moment there, I thought you all fell asleep on me. All right. Questions on anything here that we've talked about? All right, so questions about anything from class today?